To precisely dictate the optical transparency, iridescence, and plasmonic response of a surface at the atomic level, engineers rely on strict kinetic control. A plasmonic response is simply how electrons on a metal surface oscillate in reaction to light, determining exactly what wavelengths are absorbed or reflected. Achieving this level of tuning requires physical vapor deposition, or PVD, specifically the process of sputtering. Unlike thermal evaporation or chemical liquid baths, sputtering relies entirely on kinetic momentum transfer. It is a process of atomic-level ballistics. The process begins in a vacuum chamber filled with an inert gas, typically argon. A strong electrical field creates a glow-discharge plasma, stripping electrons from the argon atoms. These positively charged ions are then accelerated towards a solid source material, known as the target cathode. When these high-energy argon ions strike the target, the sheer kinetic force physically knocks surface atoms entirely out of the target solid lattice. These ejected target atoms drift across the vacuum gap. Upon reaching the opposing surface, the substrate anode, they condense, nucleating to form a thin film. Because this mechanism relies purely on physical impacts, engineers use macroscopic chamber parameters like input voltage, gas flow rates, and magnetic field strength to perfectly map and control the resulting microstructural and aesthetic properties of the final coating. The foundational architecture for this process is direct current, or DC sputtering. This setup applies a constant electrical voltage across the vacuum between the conductive target and the substrate. When depositing straightforward conductive metals, DC sputtering works highly efficiently. The constant current provides stable deposition rates and allows engineers basic control over the surface roughness and wettability of the final metal film. The system fails, however, when attempting to sputter non-conductive, insulating targets, which are absolute prerequisites for fabricating complex optical coatings. Because the target is an insulator, electrons cannot neutralize incoming positive argon ions. A massive positive charge rapidly accumulates directly on the surface, acting as a shield repelling further bombardment. This trapped charge violently discharges as electrical arcs, blasting irregular material into the growing film. Continuous DC voltage cannot reliably produce the high-purity, defect-free dielectric films required for modern aesthetics. Overcoming this charge trap limitation requires a mechanical intervention. To increase the ionization efficiency of the plasma, without simply escalating the raw voltage to dangerous levels, engineers employ magnetotron sputtering. This modification installs a specific configuration of permanent magnets behind the target cathode. The penetrating magnetic fields generate a Lorentz force. This force confines free electrons, forcing them to spiral tightly along a closed-loop path immediately above the target surface. By trapping electrons in this localized SEM, the probability that they will collide with neutral argon atoms increases exponentially. This creates a highly dense, localized plasma, exactly where the sputtering action needs to occur. The resulting increase in argon ion bombardment dramatically raises the target erosion rate. It allows the system to operate at much lower chamber pressures while producing a significantly denser film microstructure. Crucially, this magnetic confinement also traps the electrons near the target, preventing them from crossing the chamber and bombarding the substrate. This drastically lowers the substrate temperature during the deposition cycle. Magnetic confinement successfully decouples plasma density from raw power input. Engineers gain the ability to deposit extremely dense optical coatings onto highly heat-sensitive materials without melting the substrate. Beyond spatial magnetic confinement, engineers manipulate plasma physics in the time domain through high-power impulse magnetron sputtering, or HIPIMS. Instead of supplying a continuous feed of electrical voltage, HIPIMS delivers power in massive microsecond-length electrical pulses, separated by long cooling-off times. Each intense burst generates a massively ionized plasma fraction. The energy strips electrons from nearly every sputtered atom crossing the chamber. Because the pulse is brief, the target cathode does not have time to thermally degrade or melt. This highly ionized atomic flux arrives at the substrate with immense kinetic energy, physically hammering the growing film and forcing extreme densification. The energy from high PIMs optimizes the boundaries between individual crystalline grains in the film. It entirely eliminates the porous, columnar microstructures that typically cause optical scattering and poor coating adhesion. By solving the trade-off between film density and thermal damage, HiPIMS allows engineers to forge flawless optical coatings that are optically pure and mechanically robust. Control extends beyond electrical power and magnetic fields. Engineers actively modify the vacuum chamber atmosphere itself through reactive sputtering. This involves injecting strictly controlled ratios of reactive gases, most commonly oxygen or nitrogen, into the inert argon plasma. As pure metal atoms are sputtered from the target, they chemically bond with these reactive gas molecules, either during their transit across the vacuum or precisely at the moment they impact the substrate. This real-time chemical reaction enables the direct synthesis of highly functional compounds from pure metal targets, allowing for the creation of complex transition metal nitrides or custom oxides. For materials like tungsten oxide and indium tin oxide, adjusting the exact partial pressure of oxygen, the thermodynamic activity of the oxygen molecules in the mixture, directly dictates the final crystalline phase and structure of the resulting film. The vacuum atmosphere acts as a dynamic, tunable reactant. Manipulating this gas flow is the primary lever engineers use to determine the chemical stoichiometry, or exact atomic ratio, of the final surface. To steer the thermodynamic growth of the lattice, engineers rely on a matrix of three primary macroscopic kinetic dials: power, temperature, and bias. Increasing the sputtering power directly increases the kinetic energy and flux of the ions striking the target. This higher energy transfer typically enlarges the final grain size of the deposited film. Substrate temperature controls the amount of thermal energy provided directly to the growing film surface. Higher temperatures introduce adatom mobility. An adatom is an atom that has adsorbed onto a solid surface. With greater mobility, these freshly landed adatoms can slide across the surface and slot into optimal, high-density lattice positions, rather than piling up into amorphous, defective mounds. Substrate bias voltage involves applying a deliberate negative electrical charge directly to the substrate holding the growing film. This deliberate negative bias acts as an attractant, intentionally accelerating positively charged argon ions straight into the newly formed coating. This secondary ion bombardment acts like an atomic hammer. It physically peens and densifies the coating in real time, drastically altering its residual internal stress and overall mechanical hardness. Together, power, temperature, and bias function as thermodynamic steering wheels. Their precise calibration decides whether a film grows porous and rough or atomically dense and perfectly smooth. By synthesizing this parameter matrix, engineers map these vacuum variables directly to specialized surface aesthetics and behaviors. This 3D surface plot shows optical and electrical tuning in indium tin oxide. By strictly balancing sputtering power against oxygen content, engineers alter the material's properties, shifting it from an opaque insulator into a highly transparent conductor. In silver and gold films, precisely controlling the grain size through temperature parameters directly dictates the material's optical plasmonic resonance, turning standard metal coatings into highly tuned optical sensors. Balancing plasma density and reactive gases controls surface topographic roughness. This enables the creation of specialized finishes, such as tantalum oxynitride coatings, which possess a specific texture optimized for integration with biological tissue. Manipulating the phase composition via reactive sputtering yields unique high-entropy alloys and chromium carbon nitride coatings that achieve extreme mechanical hardness while maintaining highly tailored chemical resistance. Physical vapor deposition operates as a method of atomic-level ballistics, replacing macroscopic chemical washes with strict kinetic control over surface physics. Sputtering allows for the programmatic authoring of matter. By actively balancing electromagnetism and thermodynamics, engineers exert absolute control over the structural, aesthetic, and functional identity of a material.